Right. This is a video discussing synchronization in operating systems. Operating systems is not difficult. Most of the things in operating systems are things that occur in our daily lives. And so just try and link the ideas we discuss or the words we discuss with things you already know. Sorry about the music in the background, noisy neighborhood. All right. So synchronization. We need to synchronize whenever we have two or more things that are happening at the same time. Right? And if you have a computer, you have many processes that are running on it. Just as in real life, there are many people doing different tasks. So there is some need to synchronize. For example, you wouldn't just want to, start a semester where the lecturer has started but the student has not. Or let's say one student shows up at 1, another shows up at 2, another shows up at 3 o'clock. Anytime there are many things or many processes or many people interacting, there is the need to synchronize. And when we are synchronizing, it actually does imply we are sharing something. Sometimes sharing a resource, sometimes we're sharing information, sometimes we're sharing knowledge. So sharing is part of synchronization. We really can't do without sharing when we think of synchronization, right? And when we are sharing, it means that there can be issues. So there's an example here, small example where there are two bank accounts, A and B, right? Account A has 1,000 and account B has 2,000, right? Now, the one transaction wants to move money from A to B. In other words, it's going to find out whatever is in A, increase it by 500 and reduce it by 500. That's we're taking the money from A and put it into B. And the second transaction is going to move money from B to A. This means it's going to have to reduce whatever is in B by 500 and increase whatever is in A by 500. Now, if these two transactions, one happens after the other with nobody interrupting, and let's say transaction A goes first, we will have the first case where, okay, after transaction 1 works, the result would be, we would expect that A would be 500 and B would be 2,500. So this is after transaction A goes. And if transaction 1, if transaction 2 follows, it would more or less reverse what had happened before. So it would just put back 1,000 there and 2,000 there, right? Now, what if, as they were working, so you can imagine transaction 1 and 2 not happening in the same branch, but happening in different branches, right? That is the synchronization case. So in banks, this happens a lot. Someone is at, let's say, Accra branch, someone is at Kumasi branch. So the person doing transaction 1 starts off and says, well, I see, so this is transaction 1 starting, right? And he says, well, I see that A has 1,000 and B has 2,000. Well, I am going to start off by reducing this amount, right? And transaction 2 starts off and says, well, I see whatever is in A and I see what's in B, right? I am now going to reduce, since he was trying to move 500 from B to A. He says, well, I'm going to reduce by that much, right? And I'm going to take the money over, right? And this guy too can come and say, well, I also want to increase that, right? So sometimes it will work out that because of how the operations are interleaved, things are going to be working out right. But sometimes it doesn't work out properly. So for example, let's say both were saying 1,000, 1,000. This guy reduces it by 500 and is about to put almost, right, ready to add the 5,000 in there. He has it in his mind. His next thing when he goes, he's going to put 500 in addition to that, right? But meanwhile, right, this guy had also come and seen this and said, well, I am going to add, so he's also planning. He saw 1,000 there before, and he's planning to add 500. So that's what he's thinking. He said, I'm going to add 500 to that. Right. Now, if this guy goes ahead, seeing 2000, adds it in, and he also seeing this one thinks, well, I'm going to go and add this one over there. You can have a case where A is going to have 1500 and B is going to have 2500. Right? Because if you are sharing things, it's like a board, one person is moving to one side to write, another person is moving to another side to write, and you end up with transactions that overwrite each other. Right? Now, one of the reasons, okay, I'm going to give an example of how this is dangerous in real life. Now, you've seen the case where your computer says it didn't shut down properly, right? So that means, or it didn't finish installing a program. Now, often when a program is being installed or when shutting down is happening, files are trying to write and clean up their work. So if someone doesn't finish, right? So for example, if before he was going to add the 500 to this, something happened, he should be notified so he can check his work. Computers do have a way of checking. That's why when you shut down your computer or try to install something it didn't install, the next time your computer prompts you to say, you know what, something was happening when I was performing the transaction. This is just a small example of how two processes which are doing the same work can sort of hinder each other, right? Now, another common one, right, and this is much closer to computer science, is producer and consumer, right? Now, when you have a producer is something that, so a producer usually creates work, and a consumer, or let's say a producer creates some object business and the consumer utilizes the object. Usually there is some array or data structure, or usually a buffer, in which the work is placed, and the producer puts the work into the buffer and the consumer removes the work from the buffer. Now, suppose there is a buffer, right, B, with some array, right, containing some data. And there is the amount of work. It's just an int, work. It's just an integer representing how much work. Right. So the idea is anytime the producer puts in work, he's going to increase whatever is in work. And anytime the consumer takes work away, he's going to reduce the work that is in there. Now in programming, you just do work plus plus or work minus minus. But even this, that looks like one instruction, actually could be several instructions. So it means there's a variable called work. The computer is going to copy work into a register. So a register means some storage location on the processor. So let's say register 1, right? It is going to increase whatever is in register 1, and then it's going to copy the work from register 1 to a variable called work. Now this variable, whenever you define a variable, it's actually stored in memory, right? So it means anytime a computer is working on something, it has to copy it somewhere from your hard drive into memory, works on it, when it finishes, it puts it back, right? Similarly, look what the consumer has to do. He also has to go and copy work, which is stored somewhere in memory. He's going to copy work into some register, right? He's going to take whatever is in that register and reduce it by 1, and he's now going to copy work from register 1 to wherever it was in memory, right? Both of these look harmless, but remember, whenever two programs are working, there's what we call swapping. So swapping or context switching, where one program takes all the variables right, takes all the variables, whatever it's in the registers, and stores them, right? So consider this case. Let's say the work variable, right, that's in memory, currently contains 10. So I'm going to show you a case where problems are going to happen. So the producer comes and says, well, I just copied 10 into register 1. The scheduler, and we talked about the scheduler before. Remember, the scheduler moves one process, puts it in memory, brings another one to run. So as soon as producer is told, oh, you got the work variable, it's 10, you've put it in your register, all of a sudden, right, consider the consumer also comes over and says, well, I also wanted to reduce the value of the work, right? So the consumer comes and says, well, I am also going to put in 10, right? Now, if the producer is brought back, right, and he increases it to 11, and the consumer gets to run, he now brings it to 9. So there are now two cases that whoever gets, because remember, scheduling means one process could be scheduled at any time. Meaning the next thing that could happen is work could either be 11 or 9. And the question is, which one is the correct one, right? Now, in the case where you are expecting to run producer and tell producer to add work and consumer to take work, we expect if consumer runs once and producer runs once, we expect that the value of work before is equal to the value of work after. In other words, if work was 10 and producer ran, that means he added it to it, it will go to 11. The consumer can then take it, goes back to 10. Or the consumer takes from 10, brings it to 9, and the producer adds to it, takes it back to 10. But in the case we are discussing here, where the work is interleaved, in other words, the producer comes in and says, well, I saw 10, and the consumer says, I saw 10 as well. So if the scheduler moves them in and out, it's now possible for us to have improper counts. Right? Now, the only way we can prevent this is to say, if the producer starts to change the value of work, all of this should be done and completed and nobody should interrupt. Or the consumer should be allowed to finish doing this work before he's swapped out. Right? Now, these conditions or these situations are called race conditions. So race conditions mean variables are being manipulated such that the results are not what we expect. This is race conditions. And we'll continue in the next video discussing how we can prevent race conditions in synchronization.